Hello, Math 1030. This is our second to last lesson. It is lesson 12C, and both of the lessons from Unit 12 have to do with voting, representation, that kind of thing. So this lesson is on something called apportionment. Apportionment is when you have to divide on an equitable basis things that are not individually divisible. So for example, in the U.S. House of Representatives, there are 435 seats, and we need to divide those among the 50 states, but we can't, divide a seat in half or something. So we have to divide them equitably among the states without being able to have a portion. So you can't just, just divide it. We are going to focus on an apportionment method that's called Hamilton's method. There are other methods of apportionment, but Hamilton's is kind of a common one. So other things that might need to be apportioned are schools do an apportionment every time that they create a master schedule. So students sign up for classes. Well, there's only a certain number of class periods available. So for example, maybe our school offers 42 different math courses. We have to decide how to apportion it most fairly. How many sections of Math 3 should we have? How many sections of Math 2 should we have? How many sections of pre-calculus should we have? And so forth. But we can't have like 1.5 sections of a class. It has to be divided by whole number increments. Work schedules for like a nursing staff would be done using apportionment. Bus routes, they have so many buses and they have these number of routes, how many buses should go on each route, which affects the time frame for different routes of a bus. So anyway, lots of things actually do get apportioned, so it's kind of a cool topic to talk about. So this first example just has to do with our government. So the House of Representatives has 435 representatives, and it's currently apportioned based on the 2010 census. So every 10 years they do a census, and actually one census was taking place this year for 2020. In the 2010 census, our U.S. population was reported to be 309 million. So on average, how many people are represented by each representative? So to answer that question, we just need to take our population, which is 309 million, and divide it by our 435 representatives. Wow, handwriting is really good today. So 309 million divided by 435 means that we have an average of 710,000. It says round up to the nearest whole number, so 345. So we have 710,345 people per representative. On average. Okay, so it says that the constitutional limit on the House of Representatives is that the total number of representatives should not exceed 1 for every 30,000 people. So we are way above that right now. That's a lower limit though. So it's okay to be higher than that. You just can't go lower than 30,000 people per representative. If the number of representatives was set at that limit, how many representatives would there be in the House? So what we're going to do here is take our population, 309 million people, and we're going to kind of use a conversion factor here. What if we had one representative? Oh my goodness, spelling. Per every 30,000 people. And we'll kind of think of that as converting from people to representatives. So if we figure that out in our calculator, let's see. And you can times by 1 and then divide by 30,000, but it's not necessary to times by the 1. So that means we would have 10,300 representatives. I can't spell representative, apparently. Representatives. Okay, which is a lot more. We have 435. If there was one for every 30,000 people, we would have over 10,000 representatives. Obviously, that wouldn't be very effective for the government to have that many. Anyway, okay, so you'll have a homework question that's similar to that. It'll probably give you a different population. Okay, so now we're going to get into the business of apportionment. When you are doing an apportionment, we will calculate something called the standard divisor. The standard divisor is found by dividing the total population by the number of items to be allocated. Anyway. So the standard quota you calculate for a particular group, and you find that by dividing the group's population by the standard divisor. So, that will make sense once you do it. It's really not a very complicated process, just some definitions there. So the Republic of Margarine is composed of 4 states, A, B, C, and D. According to the country's constitution, the Congress will have 30 seats, and so we're going to figure out the standard divisor and the standard quota for each of the states. So to calculate the standard divisor, you do the total population and you divide it by the number of things being allocated. So in this case, our total population is 1890, and we're dividing it by 30 seats. So 1890 divided by 30 gives us 63 as a standard divisor. Sometimes we'll use the letter D for that. Okay, so our standard divisor is 63. So now we're going to come up with a standard quota for each state. So to get the standard quota, you just do the population over the standard divisor. So this one would be 275 divided by 63, which is 4.37. We're going to round to the nearest hundredth. And then you just repeat that process. 383 divided by 63. 465 divided by the standard divisor, 7.38. And the last one would be 767 divided by the standard divisor. 12.17. Now, if you add those numbers up, you should get the total of 30 seats. So I'm just going to verify that really quick. And sometimes it will be, off by 0.01 or something, just because of how we rounded. So don't panic if it is off by like a hundredth or something. 12.17. So we actually get 30 in this case. So the total is 30. Okay, so that is our standard quota for each state. So obviously, though, a state can't have 4.37 seats in Congress. That state, State A, probably should have either 4 or 5 seats in Congress, depending on how we decide to round. So the apportionment problem is this problem of rounding. How do we decide to round these things so that it is the most fair? There isn't one best method for the apportionment problem. Sometimes people will think, oh, well, obviously this is how it should be done. But there's actually pretty good arguments for each of the different methods. In this class, we only are learning one method, which is called Hamilton's method. And then we're going to look at one of the problems that arises with Hamilton's method. because all of the different apportionment methods have their own sort of problems. Okay, so here's our our standard quotas that we worked with just a second ago. So we're going to talk about overrepresentation and underrepresentation for a second, and then we'll talk about Hamilton's method for apportionment. So after the apportionment is completed, this is what they decided to do. So they decided to round this one to 4, the next one to 6, the next one to 8, and the final one to 12. So that's how they decided to apportion it. We need to complete these statements with either the word overrepresented or the word underrepresented for state A and state C. So state A is either over or underrepresented because its standard quota of 4.37 is more than its number of representatives. So the standard quota is how many they should get in theory, and this is what they actually get. So they are getting less than they should get, so they are underrepresented. And state C, this is how much they should get is 7.38, and the number that they actually get is 8. So they're getting more representation than they should. So they are overrepresented. So if the standard quota is less than what they get apportioned to them, then they are overrepresented. If the standard quota is greater than the apportionment amount, then they are underrepresented. All right, so you'll have a couple, 1 or 2 homework problems like that. Okay, so now we get to the meat of it, Hamilton's method. So in Hamilton's method, you find the standard quota for each group, and then you round each standard quota down to the nearest whole number. That rounded down amount is called the minimum quota. You're going to have some extras though. If you round everything down, you're going to have extras. You decide how to allocate the extras by looking at the fractional remainders, the decimal part essentially of the standard quota. So you're going to give the first extra to the group with the highest fractional remainder, and then if there are more extras, because sometimes there's more than one extra, you continue to distribute them to the next highest fractional remainder until all the extras have been distributed. Now that sounds maybe kind of crazy, but once you get to doing it, it's really not that complicated. So we're going to do an apportionment here. A small school district is reapportioning its 14 elementary teachers among its 3 elementary schools. And the enrollments for the 3 schools are shown in the table. We're going to fill in the table as we do our calculations to apportion it by Hamilton's method. And on your homework, it will have you enter in all of the, on some of the problems, it will have you enter in all of this data that we're figuring out on the table. So the first thing we need to calculate is the standard divisor. So remember, that's total population divided by the number being apportioned. So in this case, our total population is that there are 448 students, and we are apportioning 14 teachers. So 448 divided by 14 is a standard divisor of 32. Okay, so now we find the standard quota. Standard quota is population divided by the standard divisor. So for this one will be 197 divided by 32, which is 6.16. And then we'll just continue that process. 106 divided by 32 is 3.31 if we round. And then for Roosevelt, 145 over, 32. 145 divided by 32 gives us 4.53. Now if we add those numbers up, the 6.16, the 3.13, and the 4.53, we do get 14. So for Hamilton's method, we round all of those down. 6, 3, and 4. Everybody's guaranteed that amount. Washington is guaranteed 6 teachers. Lincoln is guaranteed 3. Roosevelt is guaranteed 4. But now we have to decide how to finish our apportionment. If we add those up, we only get 6 plus 3 plus 4 is 13. So we have one extra that we need to decide how to apportion. So Hamilton's method is that you think about the fractional remainders. Well, this one, and you won't always need to necessarily write it out. This one, I'm writing it out just to make it more visible. 0.16 is their fractional remainder, which is the decimal amount. Fractional remainder here is 0.31. Fractional remainder here is 0.53. So what you do for Hamilton's method is you look at those fractional remainders, you figure out which one is the highest, and that's the group that gets the +1, the one extra. So our final apportionment is that Washington will get 6 teachers, Lincoln will get 3, and Roosevelt will get 5. And that does add up to our total of 14. Now, this one had 1 extra. Sometimes there'll be 2 extra or 3 extra. It just depends on the situation. You're not always just deciding where the 1 extra goes. Sometimes there's more than 1 extra. Okay, let's try another apportionment. This time we don't have the table to help us, so we just have to keep track of what we're doing and think through it. So we have a city that's planning to purchase 16 new emergency vehicles. They need to apportion them among the police department, fire department, and paramedic squad, and they're going to base it on how many people are working in each of those departments. So we start by finding our standard divisor. The standard divisor is the total population divided by the number being apportioned. So we're definitely going to be dividing by 16. We need to know our total population. So we've got 485 in the police department, 213 in the fire department, and 306 in the paramedic squad. So if we add that together, our total population is 1,004. Okay, so that total is what we divide by 16. So that means our standard divisor is 62.75. Now, on our other examples, our standard divisor was a whole number. It absolutely does not have to be. A decimal standard divisor is just fine. So we have our standard divisor. So now we're going to start our apportionment. So I'm kind of making a little table here to help me keep track. We've got the police, we've got the fire, and we've got the paramedics. So I'm going to take each of those populations and come up with a standard quota, which remember is just their population divided by our standard divisor. So for the police department, that's going to be 485 divided by 62.75, which gives us 7.73. For the fire department, they have 213 members. So if we divide that to get their standard quota, it is 3.39. And finally, the paramedics, they have a standard quota of 4.88. Okay, I'm going to go ahead and erase this. So we have the standard quota. So the police department's guaranteed 7 vehicles. The fire department's guaranteed 3. Paramedics are guaranteed 4. If we round those down, we have a total of 14. So in this scenario, we're apportioning 16. We have 2 extras. So we need to decide how to apportion those 2 extras. Well, if we look at our fractional remainders, those 2 extras go to, we first look at the highest fractional remainder, that's the paramedics, so they're going to get 1. And then our next highest fractional remainder is the police department, so they're going to get 1 of the extras. So that gives us the final apportionment. The final apportionment for the police department is going to be 8, for the fire department 3, and for the paramedics 5. So that would be what we type in as our answer. So you can see, like on my first table, I had a lot more columns and I sort of formally thought it out a little more. You can just look at those decimal parts. Just make sure you distribute the extras one at a time, starting at the highest decimal remainder and then working down from there until you've apportioned all the extras. Okay, so one of the problems with this method of apportionment is called the Alabama paradox. The reason it's called the Alabama paradox is because in 1880 in the United States, they were trying to decide if they wanted to have 299 seats in the House of Representatives or if they wanted to add another seat and make it 300 seats. But what they discovered is that if they changed the number from 299 to 300, it would actually cause Alabama to lose a seat. They currently had 8, and if they added 1 more seat, the apportionment would change so that they actually ended up with only 7. So it's called the Alabama paradox. So the Alabama paradox is if an increase in the total number of items to be apportioned results in the loss of an item for a particular group. So you'll have a couple of homework problems where it gives you some scenario and it asks you to decide whether or not the Alabama paradox occurs. So example 6 is to show you how to check that. So we've got a small country with a population of 10,000. They have 3 states. We're going to call them A, B, and C. According to the country's constitution, the Congress will have 200 seats, which are to be divided among those 3 states. Use Hamilton's methods to show that this Alabama paradox occurs if the number of seats is increased to 201. So if you are showing an Alabama paradox, you do have to figure out what the apportionment would be for both of the number of seats. So we have to do an apportionment for 200 seats, we have to do an apportionment for 201 seats, and then we have to, state whether the paradox is occurring or not. In this case, it is going to occur, but in some of your example homework problems, it won't occur. So for the first apportionment, we're apportioning 200 seats. So our standard divisor is 10,000, which is the total population, divided by those 200 seats. So if we divide that up, the standard divisor is 50. So for state A, they have a population of 5,015, and we're dividing it by 50. So it's 100.3. And we just continue doing that for all of the states. Divide it by your standard divisor. This one's 90.3. And state C is a small one. 9.4. Okay, so we've got it divided out. Now we have to think about how we're going to apportion. So A right now qualifies for 100, B qualifies for 90, C qualifies for 9. If we add that up, that's only 199. So we have a 1 extra that we need to apportion. So if we look at those fractional amounts or those decimal remainders, that 1 extra is going to go to state C. So under the 200 seat apportionment, A gets 100, B gets 90, and then C ends up with 10. All right, so let's compare that to the apportionment with 201 seats. If we divide the 10,000 by 201 seats, our divisor changes to 49.75. I think it'll be okay if we round to 2 decimals there. So we have got to do another apportionment where we're dividing by 49.75. So we get 100.8 for state A. 4,515 divided by 49.75 gives us 90.75. And then our final state, if we divide that one by the standard divisor, we get 9.44, or 9.45, I guess, if we round that. So rounding down to get our minimum quota, we have 100, 90, and 9. Same minimum quota as before. If we add those minimum quotas up, we get 199. In this case, though, we have 2 extra because we have 201 seats. So if we look at our fractional remainders, those 2 extras are going to go, the first extra is going to go to state A, and the second extra is going to go to state B because they have a higher decimal remainder than state C does. So our final apportionment looks like 101 for state A, 91 for state B, and 9 for state C. So you can see that even though we increased from 200 to 201 seats, state C ended up losing a representative. And this is called the Alabama paradox. The Alabama paradox here occurred because state C loses a seat. In the Hamilton's method that we've been using, larger states or larger groups tend to benefit at the expense of a smaller state or a smaller group. So when you're doing the homework, I think there are a couple of these that you have to do. You won't always have the Alabama paradox occurring. If we had done this and C had stayed at 10 and maybe A had bumped up but B hadn't, it's possible that the Alabama paradox will not occur on some of your homework problems. So it just depends. When you finish the apportionments, you just have to compare and see. All right, so that is it. Let me know what questions come up. This is kind of a way new topic for everybody, so if it's giving you problems, for sure let me know, and I'm happy to help. Thanks so much.